Okay, so here is the important principle that we want to learn. A Dirichlet series, so you will recall that in the last couple of classes we have just been focusing on these series let's call it capital F of S. The concept that we are trying to understand is, can you treat this capital F of S as an analytic function? And towards this end, we have learned so far the beautiful things that happen in the region where this series converges absolutely. So this is the principle that we are heading towards. This Dirichlet series is an analytic function in the region or in the half plane of its absolute convergence, but actually we know something stronger. This is an analytic function in the half plane of its convergence. This is what we want to understand. First of all, so far we have learned that there is a half plane of absolute convergence. Today we will learn that there is also a half plane of convergence. To the right of a certain vertical line, the Dirichlet series converges, and to the left of it, it diverges. There exists such a half plane. So, and in that half plane, the Dirichlet series behaves like an analytic function. So far, what have we learned? Quick and very brief recap. In the region or half plane of absolute convergence, this series satisfies two very nice properties. So first of all, if the defining arithmetic function is multiplicative, then your Dirichlet series in the region of absolute convergence can be written as an infinite product, or what we call an Euler product, where each of the Euler factors is coming from primes and is of the form 1 plus f of p over p to the s. So any term in this Euler factor is of the form f of p raised to the k over p to the ks, and so on. Moreover, the other important property that we learned is that suppose you have two series, capital F of S which converge absolutely in the region real part of S greater than, say, some sigma 0, suppose you know this, then in this region capital F of S times G of S, the product of these series, can be expressed as a Dirichlet series coming from the convolution of the arithmetic functions. Where your convolution is just the sum of f of d times g of n over d as you run over all the divisors of n. So, in the region of absolute convergence itself, the series behaves in a very beautiful and elegant manner. I hope I have convinced you of the same. Now, to go to the region of convergence, first of all, that there is a half plane of convergence of the series is an important fact that we want to prove first. The fact that the series has a half plane of absolute convergence follows almost immediately by, some kind of a comparison test kind of a technique. There was nothing deep going on there. I mean, there was something deep, but nothing that's very difficult to understand. But regarding the half plane of convergence, we have to invoke some extra techniques, also very simple, but worth observing how it leads to a half plane of convergence. So, this is a nice application of the partial summation formula. So, here is what we want to prove. Suppose you have some complex number in which, so let us take S0 is sigma 0 plus IT0, and for this particular complex number, we assume that suppose the partial sums f of n over n raised to the S0 are bounded. Okay, so let us say that for each x, these sums, the partial sums of the series corresponding to S sub 0 are bounded. This is a uniform and absolute bound which will work for every x. Okay. If this happens, then to the right of sigma sub 0, the series will behave very nicely. So, here is the estimate. Then, for each S with real part, so sigma greater than sigma 0, the Dirichlet series, a certain partial sum. So, if you take n lying in any interval of the positive reals, you go over all the n's and you consider f of n over n to the s. So, these are also partial sums, but now corresponding to an arbitrary s whose real part is to the right of the complex number that you have started off with. Using this bound, you can also obtain a bound for this partial sum, and it turns out to be less than or equal to 2 times m over a raised to the sigma minus sigma 0, where a is the term to the left of this partial sum, times 1 plus absolute of s minus s0 over sigma minus sigma 0. What is the advantage of this bound? What will be helpful for us is, there is only one term here that depends on a. All the other parts here, so m of course is a bounded constant, and the distance between s and s0 has nothing to do with a, right? Similarly for sigma minus sigma 0. So, what is why is this important? Before I prove the lemma, let me tell you quick application. So suppose you have a series that converges okay, I am not talking about absolute convergence, I am saying that it converges at some S0, then for all S with real part greater than the real part of S0, the series summation f of n over n to the s also converges. So this is the generalization of the fact that you had learned for absolute convergence. This is also true for convergence, but here we have to apply this. So how does something like this follow from here? So what we do is, so notice the following. If you have that this series is converging, then all the partial sums, so what is the limit of a series? It's just a sequence of its partial sums which is converging to something finite, and therefore that tells you that the sum f of n over n to the S0 is absolutely bounded by some absolute and positive constant, right? So this convergence implies that all the partial sums are absolutely bounded above. That happens, you can apply the previous lemma, and that tells you that your the sum f of n over n to the s is less than or equal to 2m over a raised to the sigma minus sigma sub 0 times 1 plus over sigma minus sigma 0. Now notice this bound on the right hand side does not depend on b at all. Irrespective of what you take b, you will have this bound. So you can actually take n greater than a. This is the tail of your, your series. And as a goes to infinity, this right hand side just converges to 0 because no other term is influenced by a. So since sigma is greater than sigma 0, this goes to 0 as a goes to infinity. And therefore, the sequence of partial sums must converge since the tails are going to 0. So therefore, this proves that this series for any s whose real part is greater than the real part of S0, the series converges. Now let us see how you get lemma 1. This is also a very straightforward application of the partial summation technique. Proof of lemma 1. So what is going on here? So this is what we do. We write f of n over n to the s as f of n over n raised to the s minus s0 times n raised to the s0. S0 is something that you are starting off with, okay, and s is also something to the right in terms of the real part of s0. So now what you do is you let a of n be equal to your f of n over n raised to the s0, and let us take our, so let this be A of n, and so what does this mean? What you have is the following. So suppose you have f of n over n raised to the s, right? What you have is that this is equal to summation. So we are interested in the part that n runs from A to B. So n lies between A and B. This just turns out to be A of n over your n to the s minus s0, where A of n is this term here, right? So if you want to apply partial summation, what will you have? So applying partial summation, you get, so let us denote capital A of x to be equal to n less than or equal to x, A of n. So what you have is, this is equal to capital A of b over n raised to the, b raised to the s minus s0 minus capital A of a over a raised to the s minus s0. Remember, a is strictly less than b. And what else are you left with? There is an integral term that you are left with. So this is minus integral a to b with the terms capital A of t times t raised to the s0 minus s, the derivative of this dt, and this just turns out to be equal to capital A of b over b raised to the s minus s0 minus A of a over a raised to the s minus s0. And what are you left with over here? This just turns out to be plus s minus s0 into the integral a to b of A of t times t raised to the s0 minus s minus 1 dt. So far, just your partial summation formula. And now what we do is we want to give some bounds for these. So this tells us that the absolute of the sum f of n over n raised to the s is less than or equal to the sums of the bounds for the absolute values of each of these quantities. So you have absolute A of b over b raised to the s minus s0. Absolute of b raised to the s minus s0 is just b raised to its real part. You have an absolute bound for A of b. That's how you started off the lemma. It was bounded above by some number m. So you have m raised to the b to the sigma minus sigma 0. Then you have plus, remember with absolute values, the negative will become a positive. So plus m over a raised to the sigma minus sigma 0. Between a and b, you know that a is less than b. Therefore, b raised to the sigma minus sigma 0 is certainly less than, so 1 over b raised to the sigma minus sigma 0 is certainly less than 1 over a raised to the sigma minus sigma 0. So you can just take a raised to the sigma minus sigma 0 and take 2 times m, okay, and then you have plus absolute of S minus S0. Absolute A of t, again you know, is bounded above by your m, and then what you have is integral a to b absolute of t raised to the S0 minus S minus 1 dt. So, that is again t raised to the sigma 0 minus sigma minus 1 dt. So, evaluating that integral, you end up just getting, so what do you have? Absolute of b raised to the sigma 0 minus sigma minus a raised to the oh sorry, not b minus a, sigma 0 minus sigma. Again, this is absolutely bounded above by a raised to the 2 times a raised to the sigma 0 minus sigma. So, therefore, what you end up getting is this above bound is just 2 times m over a raised to the sigma minus sigma sub 0 times 1 plus absolute of S minus S0 over sigma minus sigma 0. This proves the lemma, and as an application of this lemma, you learn that if your Dirichlet series corresponding to S0 converges, then the Dirichlet series corresponding to S, as long as the real part of S is greater than real part of S0, also converges. So, when you are talking about half planes of convergence, partial summation helps you. It's not as easy as talking about absolute convergence, but not that hard either. So, this is a very, very useful and important application of the partial summation formula. So, by the way, so as I just made the remark, what this implies is that what this tells you is that your sigma, so if your sum f of n over n raised to the s does not converge everywhere, and does not diverge everywhere, then there exists a real number, let us call it sigma sub c, c referring to convergence, such that your series capital F of s converges for all sigma greater than sigma c and diverges when sigma is less than sigma c. So, this plays the sort of the role of the radius of convergence when you talk about power series. That is the analogy. Okay. With this, so therefore, the sigma sub c we call, just like we had sigma sub a, which was the abscissa of absolute convergence. This is called the abscissa of convergence. Now, here is a nice observation about the difference between the abscissa of convergence and abscissa of absolute convergence. First observation is, of course, immediate, namely your sigma sub a certainly has to be greater than or equal to sigma sub c. since absolute convergence implies convergence. So this is immediate, nothing to do here. We also observe the following. So let us say you have sigma sub c and this is sigma sub a, okay, and let's say they are not equal to each other. Okay, so in this strip, the series converges, but it does not converge absolutely. So let us take some s with the corresponding real part sigma lying in this interval between sigma c and sigma a. Okay, so what happens is that, now note that absolute f of n over n raised to the s0, okay, for any s0, so let's say if you have, I'm going to take any s0 such that your sigma 0 is greater than sigma sub c, so it's in the half plane of convergence. Okay, so if the series is converging, obviously all the partial sums are bounded above. In particular, if you just take a single n, these terms are also bounded above. So this is less than or equal to capital M, let's say, and what you have is now f of n over n raised to the s, which you write as f of n over n raised to the s minus s0 times n raised to the s0. What happens here is, so you have, this is less than or equal to m over n raised to the sigma minus sigma 0. Notice the right hand side converges when sigma minus sigma 0 is greater than 1. So now the summation 1 over n raised to the sigma minus sigma 0 is less than infinity if sigma is greater than sigma 0 plus 1. Therefore, this sum also converges when sigma is greater than sigma 0 plus 1. Now you are seeing that this is the abscissa of convergence. So anything to the right of this converges, and therefore this corresponding sums of the absolute values must converge the moment you add 1 to sigma sub c. Therefore, anything to the right of sigma c plus 1, for that the series is absolutely convergent. But this is the abscissa of absolute convergence. So what this tells you is that your sigma sub a, it must be less than or equal to sigma c plus 1. So this is the observation that if the abscissa of convergence and absolute convergence are wide apart, are different, then the distance between them can be at most 1 in terms of the real parts. The breadth of this strip is at most 1. So this is an important observation. The other observation is the following. Now we prove the main principle that we are interested in. Namely, that in the region, in the half plane of its convergence, the Dirichlet series actually defines an analytic function. This is what we are getting towards. So here is a fundamental lemma from complex analysis. I will not prove it here, I will state it. You can refer to any standard textbook on complex analysis for a proof, and those of you who are in fact following Apostle As I had mentioned, right now I am following chapter 11 of Apostle. So in section 11.7, you will see a complete proof of this lemma. So let us take f sub n to be a sequence of functions which are analytic on an open subset S of C. Suppose you also know that your sequence f sub n converges to f uniformly, uniform being very important, on any closed and compact omega contained in, you have a sequence of functions which is analytic on an open set S, but you also know that in any compact subset of this S, your sequence is converging uniformly to a limit f. If that happens, then the limit f itself is also analytic on S. Okay? Then f is analytic on S, and the derivatives, the sequence of derivatives converges to the derivative of the limit. So you can basically interchange the derivative and the limits. So f sub n prime converges to f prime on S. Of course, we want to apply this lemma to the Dirichlet series that we are talking about. You are in a half plane of convergence which you can treat as your set S, but now you have to prove the second hypothesis here. So here is the theorem that we are heading towards. Suppose you have a Dirichlet series which, suppose f sub S converges uniformly actually this is what you want to prove. In the region, in the half plane of its convergence, the convergence is actually a uniform convergence in every compact subset of the region S in C for which the real part is greater than the abscissa of convergence. So what we want to show is that this series, in fact, the convergence is not just a normal convergence, it is uniform in every compact subset in the half plane of convergence. Once you prove theorem 3, what does it imply? By lemma 2, it will immediately imply that the Dirichlet series therefore is an analytic function in the region of its convergence. So corollary, thus capital F of S is analytic in the region sigma greater than. Once you are able to treat your Dirichlet series as an analytic function, you can do lots of beautiful things. To begin with, you can differentiate it in that region. That's why we have made this observation about term by term differentiation converging to the derivative of the limit. So let's prove this theorem. Now, if you want to prove something in every compact subset without loss of generality, it is sufficient to prove this theorem in every compact rectangle in this region. Okay. So here's what we do. So suppose we have, so this is your, to the right is the half plane of convergence. Let us take a closed and compact rectangle in the half plane of convergence. Sorry, it's a badly drawn rectangle, but you know where I'm going with this. So let's say this is alpha, this is beta, okay, and the other parameters are, let's say, gamma and delta. Okay, so now what we have is, let us now arbitrarily choose. So you fixed a rectangle, choose some S0 which is not in this rectangle but to the right of sigma sub c. Okay, you can do this, whatever rectangle you may choose, you can choose some number, call it S sub 0, whose real part is to the left of alpha and to the right of sigma sub c. Let us now choose any other. So what are we trying to do? Okay, we want to show that your Dirichlet series converges absolutely in this compact rectangle. So let us take some S, and let's say your sigma is the real part of that S. All right, and now let us understand our Dirichlet series. So what does lemma 1 tell you? By the application of your partial summation, what you have is, suppose you have a less than n less than or equal to b, f of n over n raised to the s. Okay. What we want to show is that there are uniform bounds for these which do not depend on the choice of s. They will work for any s in this rectangle, right? So by lemma 1, what do you have? This is less than or equal to your 2m over a raised to the sigma minus sigma sub 0, because you know that the series converges for S0. So that is the S0 you take here, times 1 plus absolute S minus S0 over sigma minus sigma 0. Now you observe that your sigma minus sigma 0 is certainly greater than alpha minus sigma 0. So this is certainly less than or equal to 2m over alpha, sorry, a raised to the alpha minus sigma 0 times 1 plus S0 is some fixed complex number, and your S runs inside a compact interval, a compact rectangle. What that means is there is an absolute bound for S0 minus S inside for all S running in this compact rectangle. So absolute of S minus S0 is certainly bounded above by some absolute quantity. Let's call it C. So C over, and again for sigma minus sigma 0, we can bound it above by alpha minus sigma 0. Also, this bound, as we just saw, it does not depend on the right hand limit at all. Okay, so for any n greater than a, you have this bound, And therefore, as a goes to infinity, so the most important observation is that this bound now does not depend on your choice of S at all. It is dependent on your A, which is what you want for uniform convergence. So first of all, this goes to 0 as A goes to infinity, and what this tells you is that your Dirichlet series, capital F of S, I mean the question is whether the sequence of partial sums of the Dirichlet series converges uniformly to the series or not. What you have shown so far is that is bounded above by some number, some absolute number kappa, which is coming from the combination of your m, 1 and c and everything, alpha and sigma 0, times over a raised to the alpha minus sigma 0. This is exactly, this immediately tells you that these partial sums will converge to f of s uniformly, right? Because this upper bound, it now no longer depends on your choice of S. S is something in this absolute rectangle. So you have a bound in terms of that rectangle, and this tells you that your summation f of n over n raised to the s converges uniformly to your Dirichlet series f of s for all s lying in this rectangle that we started off with. Let's call this. This argument will work for any rectangle on the right of the half plane of convergence, right? And therefore, this, what you have shown is that this series converges uniformly in any compact subset in the half plane of convergence. And therefore, lo behold, you get that by your lemma from complex analysis, f of s defines an analytic function in the region where the real part of S is greater than the abscissa of convergence. So in its half plane of convergence, your f of s defines an analytic function. With this in place, now lots of beautiful applications follow through immediately, in particular applications to the distribution of prime numbers and also certain other sequences that we will study in this course. So what do you get? So suppose you have n to the s, let's say. This is analytic for some sigma greater than sigma sub c. Okay, so it is analytic somewhere, convergent somewhere, and therefore analytic there. So what you know is that you can do term by term differentiation. So your derivative of f of n over n to the s with respect to s converges to f prime of s. But what are the term by term derivatives? These are just minus f of n log n over n to the s. Basically, you are just differentiating n to the minus s with respect to s. So that is, the derivative is n to the minus s log n, right? So here is a nice formula for the derivative of f of s in terms of the defining functions for the original Dirichlet series. So in particular, suppose you apply it to your favorite Dirichlet series, namely the Riemann zeta function. So you have 1 over n to the s is equal to zeta of s. We have, because of the theorem that we learned, this is analytic when real part of s is greater than 1 in this region. It converges and it defines an analytic function. So now what happens is, this implies that now suppose you take the derivative, so minus log n over n raised to the s is equal to the derivative of the zeta function. Let us take another interesting example. This is that suppose you have capital F of s. This is lambda of n over n raised to the s. You know that when real part of s is greater than 1, this series converges absolutely, and therefore also it converges. So you have, this is the von Mangold function, and let us take zeta of s, g of s, to just be equal to zeta of s. Real part of s greater than 1. So in this region, you learnt that you can multiply the two Dirichlet series, and the term in the product would be, so the product would be the Dirichlet series corresponding to the convolution of lambda of n and 1. So what you have is that, note that. So first what you have is that capital F of s times g of s is equal to summation n going from 1 to infinity 1 over n to the s, and each coefficient is of the form summation d dividing n lambda of d times 1. This is just the convolution. What is this inner term? We learned that when you take the sum of lambda of d as you run over all the divisors of n, this basically just gives you the logarithm of n. Okay. So this is equal to summation n going from 1 to infinity log n. All of this is happening when real part of s is greater than 1, that is important. And this you derived in your previous example to be basically the negative of the derivative of the Riemann zeta function. And so what this tells you is that your capital F of s is equal to minus zeta prime s over zeta of s. By the way, the fact that zeta of s is not 0 in the region when real part of s is greater than 1 follows from the Euler product representation. I'll let you work it out as an exercise. So in this region, what you have is that your von Mangold, the Dirichlet series coming from the von Mangold function, can be written as negative of the derivative of zeta over zeta itself. This is an important identity because now what we are going to do is we are going to treat this as an analytic function and from that derive information about lambda of n less than or equal to x. So in the live session today, you are going to learn the technique of Perron's formula. We will also review it in these lectures, which tells you how to treat the Dirichlet series. So you already know the Dirichlet series can be treated as an analytic function in suitable regions. And because of the properties that come out from analyticity, you can derive these partial sums. So, you have so far learnt two different ways to study partial sums, or which lead to the average orders of arithmetic functions. One is the probabilistic approach, where you treat a function like this essentially like a random variable. That is the probabilistic approach. The analytic approach is to put this inside a generating series called the Dirichlet series and study it as an analytic function. But as we proceed further, the techniques that we use to study these sums are a combination of both these techniques. These are just at the bottom, like the base is the foundation, but whatever we do will now have a combination of both of these, including the proof of the Erdős-Katz theorem, which we have to do. Okay.